What we're going to look at now are intermolecular attractive forces and how they affect the characteristics of molecules. Whether or not a substance is in a gas, a liquid, or a solid state depends on how strong the intermolecular attractive forces are. If intermolecular attractive forces are very large, the molecules will be sticking to each other and are more likely to be a liquid or a solid. If they're very weak, the molecules will not be sticking to each other and they're more likely to be in a gaseous state. So the intermolecular attractive force determines the behavior of the molecules. Now, there are three different types of intermolecular attractive forces. There are London dispersion forces, which are also called van der Waals forces. These London dispersion forces are also sometimes called just plain dispersion forces. We also have these called temporary dipole forces or induced dipole forces. There's many names that we use for this. The most common are London dispersion forces and van der Waals forces. Polar molecules will have dipole-dipole interactions or dipole-dipoles intermolecular attractive forces, and then certain polar molecules will have hydrogen bonding. The dispersion forces are their weakest force, and then the strongest is the hydrogen bonding. The strength of intermolecular attractive forces determines the behavior of the molecules, and so we can predict whether or not one molecule will have a higher boiling point than another and things like that by analyzing the structure of the molecules and figuring out which type of intermolecular attractive force will be strongest. Dispersion forces are weak forces between any molecules or atoms. Essentially what it is that electrons in one atom or molecule will be attracted to the positive charge in another atom or molecule, the nucleus in another atom or molecule. We see this because basically there's a small dipole that is created by the movement of electrons, and that the dipole in one atom or molecule can be attracted to the dipole in another. We see this in all matter. Now, the statement here says that all covalent compounds exhibit London dispersion forces. Well, we see it even in the noble gases. It does not have to be a covalent compound. Now, although these forces are very weak, if you have a large molecule, there's a large amount of these weak forces, and they can add up to give you a very strong intermolecular attractive force. What we see is that all molecules have dispersion forces, and the force size depends on how large the molecule is or how much mass it has. Here is a picture of how a London dispersion force can occur. If we have two helium atoms come close to each other and be moving slowly enough that the dipole force here can be experienced, then what happens is that the electrons in one atom can be attracted to the protons in another. It's a temporary effect because the electron density can move or shift and not move to the other side of the atom, but what actually happens then is it induces the other electrons to move to this side if these electrons move to that side. That's one reason why London dispersion forces are also given the name induced dipole effects. This is a very small force, and it has to be under conditions where the helium atoms are moving slowly enough they can exert these forces on each other. To do this, they have to be very cool and moving very slowly. All atoms and molecules experience dispersion forces. What we see is as mass increases, the velocity of molecules and atoms decrease. Also, as mass increases, the number of positive and negative charges increase because the number of protons and electrons is increasing. Both of these things give an increase in dispersion forces. So what we see is when we have a higher molar mass, we get a higher dispersion force, which means greater attraction between the molecules. All matter has the London dispersion forces. As molar mass increases, London dispersion forces increase. So let's go on to the next intermolecular attractive force, and that is the dipole-dipole forces, or it's sometimes called permanent dipole forces. What happens here is that molecules can have a permanent dipole. Formaldehyde is an example of that. The carbon has a small positive charge on it, and the oxygen has a small negative charge on it. This is what we learned about earlier in covalent bonding when we have a polar bond. If we have two of these molecules come up next to each other, they will try to orient themselves so that the positive end of one is near the negative end of the other. Likewise over here. This maximizes positive to negative attraction, and if the molecules are moving slowly enough, they will stick to each other. Hydrogen bonding is where the next few slides are going to show you how one water molecule can hydrogen bond to several other water molecules. Notice each one of these water molecules has a dipole. Right here, this is a vector dipole showing that the hydrogen has a partial positive charge and the oxygen has a partial negative charge. As the water molecules get closer to each other, they would start trying to orient so that the positives would get closer to the negatives. Notice that in this picture, you can see the hydrogen is trying to, which has a del positive on it, is trying to get close to the oxygen, which has a del negative on it. And eventually, hydrogen bonds form. Now we show the hydrogen bonds with a dotted line because they can be detected and they are a transient force holding these in place. Notice, the hydrogen bond is drawn with a dotted line. One water molecule can have 4 different hydrogen bonds. The positive end of the water molecule, the hydrogen, has a del positive and is trying to get close and is hydrogen bonding to an oxygen with a del negative. Always orient a hydrogen bond so that the hydrogen is on one molecule is hydrogen bonding to an oxygen or a nitrogen on a negative molecule, on another molecule. It must be that a del positive is attracted to a del negative always. Hydrogen bonding is responsible for a lot of biological processes, including the helical nature of DNA and its unwinding and winding back up into the double helix. It's also responsible for the globular nature of protein and for the secondary structure of protein, which gives us hair and collagen strength. There are 3 different intermolecular attractive forces: the London dispersion, permanent dipole forces, and hydrogen bonding. The strongest is hydrogen bonding. The weakest is the dispersion forces. However, dispersion forces can grow quite large when you have a large molecule. We can recognize London dispersion forces in everything. All molecules have London dispersion forces. It just increases as the molar mass increases. Dipole-dipole forces can be recognized in molecules that have dipoles in them. If it is a carbon-based molecule, an organic molecule that has lots of carbon in it, we can recognize it as being polar when there is an oxygen or a nitrogen in that carbon molecule. An example is right here. Formaldehyde has a carbon-oxygen bond. These hydrogens are not bound to the oxygen, they're bound to the carbon, and there is a carbon-oxygen double bond. Hydrogen bonding is in molecules that have oxygen-hydrogen bonds or nitrogen-hydrogen bonds. Examples of those are water, and you can see a hydrogen is bound to an oxygen there, or something like methanol. Here an oxygen is bound to a hydrogen.